we have some late arrivals here. Your names?
Chen, C-H-I-U.
Okay, and there's some desks here. There's some here. And your name, sir?
Last name is L-I.
Yahal? Okay. All right. Quickly, just through one more. I'm waiting for Yuping, Andrew Escalante, Shetna Kumar, Lee Lin, Kim Ping, and okay. I didn't ask your name because I recognize you from your. I'm working on it. Your name, sir?
Name.
L-U-N-Y, Lin?
L-U-N-Y-U.
You better come up and just let's double check. Just so we get it right. Is that you?
Yeah, I think you.
Oh, well, they have it online wrong. Okay, but that's you. I'll fix it. Okay. All right. So you should all be here for Math48C with Mr. Schoenbrun. That would be me. We get to see if the technology is going to work. No. Well, okay. Even worse. So let me start by suggesting you jot down my website, which is Foothill. My last name, which you can look up, on the school website. And when you get to that page, you'll see there's some old courses I've taught before. I've this course before, and you can look at that if you want to. But mainly you'll be interested in the fall 2016 page. I post my notes, whatever I use to run the class, so you can find them. If you miss a class, you can go look. I'll also post handouts I give out in class, and I'll also put homework assignments up there. We'll talk about that in a bit. I'm not sure if I'm going to do it this quarter. I sometimes take videos and post those post links to YouTube where you can see what happened in class. The quality is usually horrendous, so you probably be pretty desperate to look at them anyway, but they might be there. This is the textbook for the class. They don't have it in the bookstore right now. If you don't have it, they said Wednesday or Thursday. You don't need a new copy. I can't say this very loud, but I don't tend to use the online homework system. I don't find it very useful or helpful. Unfortunately, I think they sell the book with a license to use it. So if you can find a used copy, it'll save some money. Also, since you're in C, if you haven't taken A and B already, if you had, you would have already had the book. If you just in C, you only need the end of the book, which I think it's going to be approximately chapters 6.1 and then 8 and beyond. And someone asked if they have an online version. Is that okay? That's okay. I am going to give a homework assignment today, which some of you won't have the book for. So what I'll do is I'll go home today, or certainly by tomorrow afternoon, I will scan homework and post it, so you can go to the website. I assume you're part of this class?
Not yet.
Oh, not yet.
Do you have any room?
I don't know yet. I have already two ads, have 1, 2, 3 no-shows today. The only restriction is, do we have enough desks for you? You're welcome to stay. Give me, after class, give me your name and I'll write you down. And if there's any room, you're welcome to be in the class.
Okay, all right, thank you.
And if we have to, maybe we can pull a desk from somewhere else, steal it.
In the meantime, can I?
There's a desk here, there's one here, here. Take your pick.
Okay.
If you don't like being close to the professor, it's
No, I kind of like to be in the middle, so I can see.
no problem. Yes?
So, sorry, I should have said I'm looking to get an ad code as well.
Oh, well,
Yeah, same. Okay,
you
yeah.
can be on the list to just after during the break. This is a long class. You probably know it's 2 hours and 15 minutes, but we will get a break in the middle. At about, say, 7:05, if it looks like I've forgotten, do not be rude to the professor, because, I get so enthusiastic about math, I'll just forget it and run you straight through. I know you don't want that. I don't want that either. Okay, other things. You need a calculator. Oh, yes.
Probably Brooke, I have a question, just some clarification. For 48A, I opted out for the digital copy rather than buying the physical
That's
copy.
going to be fine.
Okay, just want to make sure.
I have lots of things I want to say that are kind of rolling around up here. They may just pop out at any moment. Some of you may have noticed that this class has a very, very high percentage of international students. And I want to say this to everyone, but especially the international students who might come from a culture where they think if they interrupt the professor, that's rude. It's not rude. Not interrupting the professor when you have something important to ask, that's dumb, right? So you may need to get used to it. Also, my apologies, I'm not trying to be sexist, but some of the women, very quiet voices, and my hearing's fading. I can hear someone whispering in the back if everyone's quiet, but sometimes very high voices I have trouble with. So again, it's not rude to belt it out, okay? Can everybody hear me? Okay, good. All right. Calculator. Now, if you are planning to go on and take the calculus course, is after this, as far as I understand it, you will absolutely need a graphing calculator. So there's no reason to say, can I use this other calculator? Someone asked me already. On the other hand, if this is your last class, let me tell you what you will miss by not having a graphing calculator. You will not have a nice function that will just graph the trigonometric functions that we're going to learn, and that's going to be one of the things we need to learn how to do. Hello, your name?
Yuping.
Yuping?
Yes.
Okay, nice to see you here.
I'm sorry I'm late.
There's some seats in the front if you don't
Okay.
see any in the back.
Professor.
I
I also worked in
Oh.
Last name is Kumar.
Kumar. Oh, okay. Yes, check. Okay, thank you. Yeah, so the one way you could get around that, there are alternatives. For example, this isn't going to work, is it? I guess what I have to do to make this work is I have to go to my system preferences and tell the screensaver, not the screensaver, not 20 minutes. Never. And then I reset this whole thing. And then hopefully it'll all work. Did you just arrive?
Yeah.
Your name is? So, the only person not on the list, who's not here is Andrew Escalante. Andrew's still not here, okay. There's a chair right up here. I know it's scary to be this close to the professor. But you know, through osmosis, you might learn math after that. Okay. Okay, so just basically, if everyone here has taken a class in, we call it advanced algebra and geometry, is that a fair assumption? If you haven't, you're going to probably have to work a lot harder and do some review on your own. I want to, even though you've taken this class, I want to go over some really basic geometry because it's so fundamental to what we're going to learn. So let me start with a few definitions from basic geometry. Can someone tell me what a line is? Remember what a line
difference
is?
between two dots?
Okay, between two dots,
Set of dots.
we call that a line segment.
Line segment.
Okay, but a line, two dots will determine it,
But it's
but
infinite.
it goes on forever. Okay, that's a line. A ray is kind of like a half line. You have a starting point and a direction, and it goes on forever. I also, you know, we do these drawings so often that I want to make something clear. This is something I impress on geometry students, but this is just a drawing, a representation. The line has, and the ray and the segment has no width at all. So I can't really draw it. And the points, they're not little dots, they're just locations, right? So just to be clear, this is just a representation that we use. Use it so often that I worry that students might misunderstand that at some point. Okay, so we have a line segment and a ray, and this brings us to, let's see, I didn't consider the possibility here. We have an angle. And we define an angle as two rays with a common endpoint. Now, we're going to use the term angle in a few different ways. One is, this is the most basic definition, but sometimes what we really mean is the measurement of how far apart these angles are. Technically, I should always say the angle measurement, but I won't. And you should be able to figure out in context. Okay, just a few more basic things to remind you from geometry. We have a triangle, which consists of 3 line segments. It's determined by 3 points that are not on the same line or line segment. They're not collinear. And in particular, there are a few different types of triangles you should know about. The first is an isosceles. What's an isosceles triangle? Anyone remember? Isosceles triangle? Yes?
Triangle that has two sides that are the same length.
2 sides that are the same, right? very good.
Can you write down this word, please?
I will. And I'm going to proceed it by saying that whenever I write it down, my word processor corrects my spelling.
It's okay, I will not see your mistakes.
ISO, meaning the same, I think it's a Latin or a Greek root. Isosceles, I think that's how you spell it. At least if it corrected it on my paper here. So we have an isosceles right triangle, which has some very predictable proportions. For example, if the legs, those are the sides that are not the third side, the third long side. Does anyone remember what we call that? The third side of a right triangle? Hypotenuse, yes. I know I'm going to spell that wrong, so I'm not going to try. If the legs were each one, then the Pythagorean theorem would tell us that the third side is
Square root of 2.
square root of 2. So this triangle will come up. The second triangle, this is isosceles right triangle. A right triangle being one with a right angle. Next we have an equilateral, equal, lateral, equal meaning the same, and lateral meaning side. So triangle with all three sides the same. I didn't spell that very well. And does anyone recall what the angles of an equilateral?
60
60
degrees.
degrees.
60 degrees, that's right. We know that because they have to all be equal,
One.
and their sum has to be 180. Very good, yes. Okay, there's one other triangle which really isn't going to come up, but whenever we go over these triangles, I think everyone should know about it. It just is this nice triangle that happens to have sides of predictable length. If the legs are 3 and 4, then the hypotenuse is 5. Right. This is really interesting, I guess, when you're taking the SATs, but it's not really that interesting for this class. Okay. Let's see if I can get this going again here now. I will say also this. Today is probably going to, some of you will say, wait, this is really slow. And it is, there's a bit of review, and we don't want to lose anybody on the first day, of course. But it will get harder, I assure you. Okay. Question? Yes.
I have heard like the 48C is kind of like first step for the calculus courses. So like we're gonna study more calculus things before once.
We're not going to do any calculus. We're going to do mostly trigonometry and some polar coordinates, which come out of trigonometry. We're not going to do any actual calculus in the class, but all this subject matter becomes very important when you're taking calculus, because as you get into the calculus class, you're going to use the trigonometric functions. You're going to use calculus on them. So if you don't know that you're trig real well, I would not skip this class. If you do, you could consider that. There's still time. This, yes, good morning. Okay. Or they're just not going to work for me, because that would be the thing to do.
Can you unplug?
Can I help?
Can you unplug and plug back to computer?
Okay, thank you, that's a good suggestion. Yay! Uh,
That's a MacBook known issue.
oh, okay.
When it go to sleep,
I was up in this room a year ago, I don't remember that problem, but I think we're just gonna switch over to here for now. Okay. And I have to switch this over too, so I can see what I'm doing. Okay, so we talked about an angle, and now we're going to talk about angle measurement. In basic geometry, we treat this as just a certain value without any direction. And we're going to add to that today, but first I'm going to remind you that we divide an angle up into a unit such that a complete circle would have what kind of measurement? 360 degrees. Now, does anyone know where that strange number 360 comes from?
from radians? From, I don't know how you spell it. Radians?
Radians?
Yeah, like 2p.
We're going to learn about radians, but degrees comes from way back in history. That's right. The Babylonians used a base 60 system. All right, you probably know we use a base 10 system. Base 60 has a nice property that if you don't have a good way to write down numbers, the way we do, well, the advantages are it's very easily divisible. Divided by 2, 3, 4, 5, 6, and 10. Right? And many things in our world today continue from that period. Does anyone think of anything we divide up into 60?
Time.
Time, yeah. Minutes and seconds. Hours, well, there's a 6 in there. Okay, but that's where it comes from. This is not the only set of units that we use to measure angles. There's an entirely different set of units called grads. Grads divide a circle up into 400 units, and I'm not quite sure. I'm not quite sure where it's used. It's used in some kind of industrial applications at times. The nice thing about 400 is a quarter of a circle, a right angle gets divided up into a number we like, 100, because we're base 10. I just mentioned that in passing. But now we're going to get on to a unit which is very strange, especially if you haven't run into it before. It's called a radian. And I'm very carefully, I'm going to call it, it's a very natural unit. All right, so now first let me show you why you have a good argument that it's not very natural. We divide a circle up into 2 pi radians. Now, any of you who know anything about pi, you know it's a long decimal number that goes on and on forever. So this doesn't actually seem like a very good unit or even natural, but I'm going to try and convince you otherwise. So 2 pi radians, that would be
180 degrees.
6.28 and
Do we convert radians to degrees, like 2p radians?
We will learn how to convert radians to degrees
Okay.
today. Yes. This is one of the skills you're going to learn in this class today. I just want to kind of argue by badgering you a little. Does anyone remember some other function that maybe you learned in A or B that uses the word natural?
Natural logs.
Yeah, logs, yeah. So you have like a log to the base 10, right, or something. And then we have the natural log, right, which is the log to the base E, right, which is also a kind of a crappy number, right? And then 2.71828. It's almost like a pattern there for a second, but it doesn't go on very long. So I'm just trying to convince you that you can have a very crappy looking number, but it can still be quite natural. Okay, so here's how we define a radian. We're going to take an angle here, and we're going to draw it inside a circle that has a radius of 1. I don't know why this S is here, that's a mistake. And we're going to measure the length of the circle, or the section of the circle that this intercepts here. And we're going to call that the number of radians. Now, this definition works if you have a circle of radius 1. If, on the other hand, you have a circle with a different radius, such as r, then the number of radians are s divided by r. Now, why is that the same definition? Well, all circles are similar. This object, this section of a circle here, right? If it has the same angle, then it's similar. And again, you may recall from geometry that objects that are similar have proportional parts. So the ratio of s to r, in the case of a radius that's not 1, will be the same as the ratio of s to 1. It's just going to be that same value. And that's what we call the radians. Now, just to be very clear, if you have a circle of radius 1, what's its circumference? Well, how do we figure that out? Well, circumference is pi times the diameter. The diameter is 2r, so it's 2 pi r. So if the radius is 1, the circumference must be 2 pi. All right. I want you to get used to the idea that 360 degrees is equal to 2 pi radians. Okay. All right, we're going to use that fact, and we're going to look into this subject that we were talking about, which is how do we convert? We're going to switch blackboards here. Let's think about this. I can give you a formula, and some people like to memorize formulas. I much prefer that you understand where the formula comes from. That way, when you're doing the test and you forget the formula, you just go, well, Mr. Schoenbrun showed us how to figure this out, so let's do this. So we know that 360 degrees is equal to 2 pi radians. That's the whole circle. Right? So if I were to take an angle, let's say a very simple angle of 60 degrees, and I want to know how many radians that is. Well, we know we want to multiply it by some factor, right? Did they discuss in a previous class something called unit analysis? No. Okay, digression here. Let's say I wanted to convert centimeters to meters. So I have some number, 5.67 centimeters, and I want to multiply it by something, and I want to get meters. So what unit analysis says is treat the units kind of like they're numbers, right? So I have centimeters, I want to get rid of meters, so I want to multiply by meters over centimeters, right? The centimeters will divide out, and I'll be left with meters. So then all I need to know is, how many meters are there in a centimeter?
1,000.
1 over
Hundred.
100. 1 over 100. 1 over 100.
1 over 100. Okay. So that's what unit analysis is. If people have questions about that, let me know and I'll spend a little more time with it. Let's do the same thing over here. We have degrees. We want to multiply it by some factor. We want to end up with radians. Well, we know 2 pi radians is the same as 360 degrees. That is to say, this is a representation of 1, right? They're the same, so the number isn't 1, but this is like multiplying by 1. Except that here, the degrees cancel out, and we're left with radians. So this is our factor, 2 pi over 360, which we multiply degrees by to get radians. Now, you could say, wait a minute. We could just use pi over 180. That's true. If you want to remember that, that's fine. That works. It's just, for me, it seems harder to remember that. I have to remember pi is a half circle, 180 degrees is a half circle. But this will work. Okay, let's go back the other way. Let's say I have, well, what is the answer to this?
2 over 3 pi radians.
Pi over 3. 3. Okay. All right, let's go the other way. Let's say we want to know what pi over 4 is in degrees. So we're going to multiply it by the reciprocal of this, right? 360 over 2 pi radians, right? This is radians. The radians will drop out, and now we just have to multiply 4 pi by 360 over 2. So that's 180 divided by 4 is 45 degrees. Just use the degree sign here. Okay. All right, so let's take a look at this. Let's look at some values here. 1 radian is how many degrees? Well, 1 radian, we're going to multiply it by 360 over 2 pi radians. We're just going to get 180 over pi. I think it's worth noting at this point that 180 divided by pi is just kind of a weird number, right? It's 57.29, and it goes on just because pi is going to go on forever, right? Okay, so 1 radian, it's not that, it's a little smaller than 60 degrees, is 57 degrees. All right, now 1 degree, how would we find out 1 degree? We'd multiply 1 times the reciprocal, 2 pi over 360, or pi over 180. That's 1 degree, and again, we're going to find pi divided by 180 is again kind of a useless looking number, 0.01745. We're not normally going to work with decimal equivalents for radians. Occasionally you'll do a real world problem and you'll get out your calculator and come out with something you'll have to round it. Okay, let's take a look at these other examples. These are going to be important. The better acquainted you are with these conversions, the easier a lot of things will be. Let's first look at 30 degrees. How many radians in 30 degrees? So again, 30 times 2 pi over 360. So that's pi over 6. Okay, that makes the next few of these real easy. 60 degrees is obviously doubled, so twice pi over 6 is just going to be pi over 3. 3 times this is just going to be 90 degrees is pi over 2. And then finally 120, that'll be twice 60 degrees, that'll be 2 pi over 3. Okay. So this is something, this is not a big deal, but you're going to have to do this now and then in the class. You have to convert between radians and degrees. I guess this would be a good time to give you a little practice. So, look for the handout. This. Going to have you pass these around. I'm not going to forget you. Let's start passing these around. And I have some more. And when you get it, just take a look at the first page and start passing. All right, if you just take a minute, take a stab at the first page.
Excuse me?
Can I get a copy too? Excuse me?
Yeah, you can have
$7.
Just pass the next one.
One more? Who do you, one more? So one more?
Oh, okay.
Who needs one? Okay.
I don't want to hit the camera.
Do we need to do on the first page?
I'm sorry?
On the first page?
Yeah. Got a question? Oh, just the first page, yeah. See the problem. All right, is anyone having any difficulty with these, or is there any particular problem that was a troublesome?
Yeah, I always forget to divide by 2.
Forget to, oh, 2 pi 360, 1 pi 180.
Somehow, I remember that 360 is p, not 2p. So, and that's probably a mistake, and I'm doing this again.
Well, now's your opportunity to fix that, right?
I never got explained what is radians actually. So,
Okay.
this is much easier.
Okay. Yes.
Isn't it easier to divide 5 over 180 instead of 5 over 360? Could we still get the same?
Yes. If you will remember that accurately, it is easier. What I find, it's easier to use it. What I find is, do you remember that pi over 180 is the factor? And here, what I'm trying to show you is that it's easy to see 2 pi is 360. From there, you can easily go to pi is 180. Right? That's all. I'm examining this at a very low level of, you walk into the exam and you're nervous, right? And you're not thinking clearly, and then suddenly I need the factor. What is it? Right? So this is a way to reconstruct the factor or to remember it. That won't fail you, right? Okay. All right. I guess I'm actually looking for feedback from you. Is it easier if I put stuff up on the overhead or draw stuff on the board? Does it matter? Anyone have an opinion? No opinions? I saw a hand.
Oh, no.
I know, you're just over here. Okay, all right. Well, we'll try this. Okay, so let me give you a little different problem. Let's say I have an angle of, say, 70 degrees, and it intersects a circle of radius, or maybe one circle, of radius 5. So what is the length? What is the length of this sector of the circle that's intersected? Well, it turns out that it's much easier to figure this out if instead of degrees, you're dealing with radians. So let's first convert our 70 degrees, and I will use the suggestion that instead of 2 pi over 360, we're just going to multiply it by pi over 180 degrees. And now we have radians, okay? So now remember that the radian measure was this length, the radian measure. Is everyone familiar with the Greek letter theta? Okay, we're going to use theta a lot. We're going to use other Greek letters in this class, but theta typically is going to be an angle, and in this case it's in radians. So it's that S over R, radius. Well, that means S, of course, is equal to R theta. So since this is our radian measure, we just multiply it by the radius, and we're going to get that length, S. Now this is a problem for a calculator, right? So 70 times pi divided by 180, and then times 5. And we see that the length is 6.10. Again, we're going to get these long decimals. We're not going to get anything clean whenever we're dealing with circumference of a circle. Okay, let me ask you a different question.
Professor?
Yes.
Sorry. From where you got number 5?
Radius? I just made that up.
Oh, okay, so you just created.
I just created a circle, radius 5. Oh, sorry. You're going to have to point this out to me. Sometimes I'm not always as
Good.
on top of this. Okay. Lovely hand-drawn circle there, right? Okay. All right, so has everybody got all that? Because now I'm going to ask a little different question. What is the area closed here?
Sector?
Yeah, that sector. What is the area of that sector?
What do you mean?
What do I mean by area?
Yeah, what do you mean by that?
Okay. Let me just back up just a brief minute. All right. So if I had a square
Yes.
and its sides were 1,
Uh-huh.
the area of this
Okay.
square would be 1.
Yes. Okay.
If I had a circle,
2p r squared.
I had a circle with radius
1.
2, right? The area of that circle would be
8p.
pi r squared, which would be
Ah.
4 pi. Okay, is that clear?
Yeah.
Okay. So now, I want to know what the area of this sector would be. So how would I figure that out? Any ideas? Okay, well, let's do a simpler problem.
So, I'm sorry?
I said, let's do a simpler problem.
No, will it be the same but multiplied by r squared? Not by 5, but by 20.
Well, that's going to come into this. Yes. Let me give some simpler problems. Often in mathematics, when something is presented to you and it's confusing and it's difficult, sometimes if you look at a simpler problem, you can get an idea of what the more complicated answer might be. So let's start with a circle, and its radius is 5. And what would its area be?
2 PR squared divided by 4.
It's just going to be pi r squared, right? So 25 pi. Now, if I take that circle and I divide it in half, so this was a complete circle that was 360 degrees, but I'm going to cut it in half, so now I'm only looking at, say, 180 degrees. So what's the area going to be? Well, it's going to be 25 pi, but divided by 2. Let's keep going here. We're getting a little more complicated each time. Okay, now let's take a circle and let's divide it into quarters. And now we're looking at a 90-degree sector. Well, again, it's pretty simple, right? It's just going to be a equals 25 over 4 pi. So here, like, there's a factor of 1. Here there's a factor of a half. Here there's a factor of 4, 1/4. So if I now take this next step and I say, okay, let's just jump. Now it's a 70-degree angle, like our problem. Well, now we have to think about where did that 1/4 come from and that half came from, and the 1. Well, here, clearly 360 divided by 360 is 1. Here, 180 divided by 360, the amount of the circle we want the area of, that's a half. Here, 90 over 360 is our 1/4. So it might be a good guess that we can multiply 25 pi times what? 25. Sometimes I say one thing and write with the other, right? That means there's an alien being controlling my right hand, and I just thought it. All right, so what are we going to multiply that by? 70. Now here's another place where unit analysis comes in. 70 degrees over 360 degrees. Well, the degrees kind of cancel. It's just a fraction. Right? And now this is a number we can, either leave it the way it is, or we can plug it into the calculator and get an actual number. Okay, so those are 2 different types of problems you can solve now. You can find the length of a sector of the intercepted arc. That's the word, the arc. Or you can find the area of a sector. Yes.
Just turn the page.
You want me to turn the page?
Yeah,
You
like
could-
the one where it was.
Right. And what I'm going to do now is I'm going to ask you to turn the page over. And we're going to have a break now for about 15 minutes. In case you're not familiar, just around the corner there's a little cafe, which I'm not sure if it's open now. But we'll find out.
Either 7 or 7:30.
Yeah, if they're open at 7:30, you can still get coffee. But when you come back, fraternize with your newfound associate students and work on the second page. Take a look at that.
Why?
Oh, you want to take a picture of it?
Why?
You want the one. But I think
That's okay.
I'm using what I can.
What? We all have to, oh. 21 over 2, over 12, okay. My brain isn't looking long enough to check that, but assuming that's correct, so you multiply the radian measure times the radius, which is 11.5. So that would be, all other things being equal, that would be correct. So I can wait for everybody. Everybody's back.
And I have Canada plan for. Oh, what's up, man?
Yeah, are you?
And I have Canada planned for.
Oh, that's cool.
So yeah.
Good luck.
You excited about that?
Oh, we have to do the thing? I see, okay.
Did you find a chair?
Yeah.
Oh, okay. Who are the, there were two people I think you wanted to be put on the, yeah, come on up and give me your name. There were two people. Yeah, okay. So your first name is, M-I-L-C-K-B. And your name is? Peter.
Well, like, I'm gonna wait this one.
So there's one person who did not, who is registered, did not come today. He told me he got stuck at work. So if you all have desks, and I think we just need one more desk. So I think that would be okay. I'll bring an ad on Wednesday. Yes. I'll hang around after class if you want. That would be fine. Okay, I assume it, almost everyone's back, everyone should be back. So I have a few random thoughts I want to share with everyone. I guess you may have noticed, again, sometimes I have a little trouble with hearing, so I may want to do something about that. I may want to try and, normally I don't have a problem, but if a big echoey room like this, with, very soft voices in the back, sometimes I have trouble So bear with me on that. I have a comment or two about worksheets and homework. The purpose of worksheets in class and the purpose of homework is practice, right? I do want you to do your homework. If you look up on the green sheet, you'll see I give you a certain amount of credit for doing that. That's not for getting the problems correct, that's for doing the problems. Right? Again, it's practice. I want you to do the homework. It's to your benefit. If you're just stuck in this class and you should be in a calculus 3 and they're making you take it, and you don't do any of the homework, you can still ace all the exams and get an A. So it's unlikely there's anyone in that situation here, but if there were. So again, I wanted to say, I will want to see your homework, but you don't have to stress out about it. It certainly makes no sense at all to ever be someone else's homework. That would be cheating, and you would be cheating yourself. That's not to say I encourage you, if you wish to work with other people on the homework, there's nothing wrong with that. What you hand in should be your own work, of course. You should hand in things you understand. And as I said, it's not crucial that you get everything 100% because that's the purpose of homework. As far as grading you, that's what the quizzes and the tests are going to be for. There will be 4 quizzes this quarter, and there'll be a midterm and then a final. The midterm and final will take a good portion of the class. The quizzes will be, maybe a quarter or a third of the class. And I know everybody can have a bad day, and so if it benefits your grade, I throw away the lowest quiz. So that can help. It also helps every once in a while something comes up and they can't make it for class and they don't have the kind of excuse that I can just say I'm not going to count that at all, but you get a 0, but then you get to throw it away. So you're safe for at least one of those. I don't want to say much about cheating other than don't do it. It's usually obvious. I don't think I've ever had a problem. I think I've had a couple of cases of it was obvious people were copying homework, and they didn't like that, but that didn't bother me. Academically, it doesn't help you. It serves you very badly if you get caught. And again, I don't want to say any more than that. You look like you're adults here, and I think you understand. If there was anyone in class who comes under the category where they have some disability and they need some accommodation, obviously that's a private matter, and you can either email me about it, or if you come to my office hours, if you want to have a private conversation. I'm always going to be here at least half an hour before class. I'll probably end up being here an hour before class pretty often, just the way my schedule works. So if you need to talk to me about something like that to make arrangements, let me know. Okay, any questions? Let's go back to the overhead. I have a little video. It's kind of corny, but I'm downloading it. I don't know if it's going to get here in time because of this internet, but we'll see. Are there any questions about these problems? The final length of the arc. Guess I thought there were going to be some area here. I guess there weren't any. There will be on the homework. There'll be some problems with the area of the circle. Yes.
Question. Any chance that we can find there's worksheets, online, somewhere.
Yes, my website.
Nice, thanks.
Okay? That's this website, and in general, anything I hand out in class, if it fits that. Oh, and let me say something about the homework. The homework assignment is listed online. I may modify it by the end of class if we don't finish the class where I thought we would. There's a fair chance of that. But some of you may not have the book. Anybody not have the book? Yeah. I'm going to go home tonight, because it's not available in the bookstore till, say, Thursday. I'm going to go home and I'm going to scan the pages that the homework was on. So you'll at least, if you want to work on that, you'll be able to, it'll be obvious on the website. It'll be, homework problems or something. And I'll either get to that by tonight or tomorrow afternoon. So you should have a chance to work on it. Yes?
For our homework, should we simplify everything down to decimals, or should we just leave it in fractions?
I'm so glad you asked that question. It's a big topic here. It really is. Okay. So let me talk about that for a minute. The way I look at it, there are two types of problems you're going to get in this class. There are going to be real-world problems where I say, I shot a missile, at 45.7 degrees, at such and such velocity. When you see a problem like that, it kind of begs you to take the numbers when you're done, pop them into your calculator, and this isn't a science class, so I'm not going to be picky, unless you should know how to round. If I say round to 2 decimal points, you should know how to do that. But most of the problems in this class are going to be of the kind where you're going to end up with an answer like 37 pi. Please leave this just the way it is, right? It's a number. It's an exact number. This is a math class. One of the things we do is sometimes we deal with exact numbers. So, am I making sense here? It's possible. See, something happened about 25 years ago when you were able to buy a calculator for $10. And I know these are a little more expensive than that, but you could buy a cheap calculator, which is all of a sudden students started getting really good at punching buttons and not knowing what they were doing. And sometimes I don't know what I'm doing when I'm punching buttons. And for certain things, that's fine, right? If you're out there at the races and you're calculating odds and whatever, that's fine. But along with that, students kind of lost sense of numbers. So, they pump some digits in and they come out with a number that made no sense at all for the problem. And they wouldn't realize it. So, I think that, let me tell you something you won't find on any of my quizzes. I'm very careful not to give you a problem where the numbers just scare the crap out of you, where you end up with something like, the square root of 1647 times pi over, some, 3/47, something where just trying to simplify that, your brain kind of starts crawling. That's a skill, but that's not the skill I'm trying to teach in this class. We're trying to learn trigonometry, functions. So I'm not going to try and fool you. I'm not going to try and scare you and rattle you when the quiz, on quiz day or test day. But I would like you to understand that, well, okay, that's a number. if that's what the problem, well, okay, probably put the 47 on top, right? Right. Multiply by, divide by a fraction, multiply by the reciprocal. You should know that kind of basic stuff, and you know, let's see if I 225. Do we know what the square root of 225 is? Very good. Okay. See, so you know that it's nice to know that. Maybe you want to use your calculator to see if that works, but otherwise, just leave it. Okay. I don't expect this issue to be completely clear yet, but I will, you know, when things come up, ask questions, and I'm going to probably at different times I'll explain, you know, when we're doing a problem, well, this is what I expected. In general, if you see like some of the numbers have decimal points in it, then it's probably okay to use your calculator and just give me some number that pops out of it after you've looked at it and said, well, does that make sense? Okay, all right. Back to the worksheet for a second. Are there any other questions about it? I didn't make up these problems, so some of them may be ugly and scary, but hopefully not. Yes?
We changed the feet to meter, right?
Oh, did they make you do that?
Should I make it? No. Should I just keep it feet, or should I change it to centimeters or meter?
Okay, in general, you should know how to convert units. If I don't ask you for it in a certain unit, you can do whatever's easiest for you. I generally will stay away from a metric to English system conversions because I imagine if you're going into science, you're just going to use metric anyway, right? That's I mean, you know, that's part of math, but it's not part of this class, is what I'm trying to say. So don't worry about that kind of stuff. If something comes up like that, call me on it and say, you said, you know, you weren't going to do something confusing like this, and I plan not to. Some of the problems in the book may violate that idea. But... Okay, yes?
We go back to the homework topic for a second.
Mm-hmm.
So it's not going to be a homework that we submit online. We just take the papers here.
Yeah, you just hand out
to
some
you.
papers, and I understand, you know, you don't have to raise your hand. Is there anybody in this class because like they work? Yeah, there are. Oh, there's quite a few. I understand. You got a job. The pace of the class doesn't always fit the pace of the job perfectly. We have Monday and then Wednesday, and then you have a long break, right? So, you know, try to do the work, you know, when I ask you to, because then you'll be more in sync with the class. But if you hand something in late, that's generally fine. I'd rather you not wait till the end of the class and hand me all your, you know, homework. That would be troublesome. But you know, okay. Other questions? Yes.
Can you just do one of the problems?
Do you want to pick one?
Can I pick?
We can do two problems. You can each pick one. Number 2. Okay. See if I can do this here. This is the problem. Okay. So the problem asks. We didn't talk about this yet. I have to admit. We didn't talk about what it really means to have an angle greater than 180 degrees. We're going to do that in a few minutes. But the idea here is we have an angle of 270 degrees. That's the size of the sector. And we're going to use that formula that S equals R theta. Theta has to, for this to work, theta has to be in radians. So let's convert our 270 degrees. 270 degrees times pi over 180, right? So those both look like they're divisible by 90, aren't they? So that's going to be 3 over 23 halves, 3 halves pi. Okay? That's also a good number to know that 3/4 of a circle is 3 halves pi. So we're going to now plug that in. That's our theta, and our r is 13 feet. So 13 times 3 halves pi is going to be 39 over 2 pi. Okay, now I said as things come up, I'm gonna bring them up. Some of you may be tempted.
What's 13?
13 is the number they give you for the
Isn't
radius.
it 19?
No, I thought that too. It's the-
No, it's the,
Okay.
I guess it's poor. You don't have to worry if that's the error, that is because it's a poor quality reproduction here. Then your answer is just as correct. So some of you might be tempted to, instead of writing 39 over 2, you might write what? 19.55. Now, I won't have a problem with that, but I encourage you not to. I encourage you not to. Something I used to tell my high school students when I taught high school was, fractions really are your friend, right? You know, because you don't know in the next step you may multiply this by some even number and then the 2 is going to disappear and then you didn't need that decimal. I'm very happy with a fraction, even a fraction that isn't reduced to lowest terms.
Can I ask a question?
Sure.
Like, what is the meaning of the rounding your answer to the nearest tenth? I don't
Oh,
know.
well, the meaning of that is that I copied this from somewhere else, and that's what their instructions were. So they actually want you to multiply 19.5 times pi, and, okay, now you don't know what it means to round to the nearest tenth. Okay, good question. So let's do this problem just the way they wanted you to do it, not the way I care. So let's say 39 divided by 2, okay, 19.5, just as we expected, times pi. Okay, so now we have the number 61.26105675, and that's not exact either, right? We know that. So to the nearest tenth, that's the tenths, 0.2, right? So we want to round that. The number below it is above 5, so we're going to make that 61.3. That's what rounding, how we would round that. Now, if this were 0.50, some people round even, some people round up. I don't care. As long as it's above 0.5, you round up. If it's below 0.5, like it's 0.498, then you round down. And again, this is not a class in rounding. I'm not going to be that picky about it, or that, you know, if I was being picky, you know, I'd say round to the nearest tenth, and then I'd take off a point if you did that wrong, because I don't really care. Okay, let's just ask a few simple questions. You know, if I said round to the nearest integer, what would this be? 61, right? If I said to the nearest hundredth,
61.26.
0.26, very good, okay. If you have trouble with rounding, you know, again, office hours or during the break sometime, we can go over it in more detail. Okay, I'm just going to interject something. I've noticed that, you know, people have gone in and out of the class, during class, so they came in late. And that really is okay. You're adults. If you need to do something, you know, take a call, do a text, fine. I appreciate the fact that everyone so far has been doing that, has been very quiet about it. And that's all I really ask, not to disrupt the class. And if you need to go, fine. If you need to leave early, fine. Okay, are we ready for some more material?
Excuse me, can you just clarify for me, is that, for question 4, is that x or pi?
That's a pi. Yeah, I'm sorry. It's probably a copy of something that was scanned. So. I won't do that to you on an exam. All right? All right. So we're going to talk about something called a directed angle. But before we talk about a directed angle, I want you to think a little bit about something you already know about. We mentioned something called a line segment. And if you take a line segment and put it on an axis, and you put the left endpoint at 0, so now you have kind of a directed line segment. In other words, it goes from 0 to 5. That is a topic we're going to study in this class much later. There's a nice term called a vector. I'm sure you've heard of the word vector somewhere. You know, you're up in an airplane and you're listening to the captain. And vector 47.6 degrees, right? We're not going to do that now. But you see the idea that a line segment could have a direction, right? In this case, it's pointing to the right. And we treat that as a positive direction. It's arbitrary. If we were to take a line segment going in the other direction, we would treat that, we would say that's negative. And we're going to look at the same kind of idea with angles. Okay. So the first thing we want to do is we want to put an angle in what we call the standard position. What that means is that the vertex is at the origin, and one of the rays is along the x-axis. And that's what we call the, oh goodness me. I'm not all that concerned about the terminology. But the book is, so I should be. Well, I don't have the terminology. It's the starting ray and it goes to the end ray, right? And there's a direction involved, right? This angle could be in this case it's an acute angle. Could be a 90-degree angle, or as you can see here, it's an angle that's greater than 180 degrees, right? Because to get from this ray to this ray, we go around this way. And because we're going counterclockwise, we treat this as a positive angle. Now, here we have what looks like the same angle. It's an equivalent angle, but in fact, here we go and we're going around in a clockwise direction, so this is a negative angle. This is, what's that angle? It's 90 degrees, 45, negative 135 degrees. Or if you prefer radians, it's going to be, looks like negative 3 pi over 4. I think that's right. Okay, it's possible that two angles, such as these, this angle and this angle, have the same rays, and they're called coterminal. I feel the need to draw this. So here's my starting ray. I could have an angle here like this, or I can have an angle here like this. Or I might have an angle that goes completely around and ends here. These are angles that are equivalent, but they have different values. Now, everybody put on their thinking caps. These are called coterminal. What can I say about the difference in angle between two coterminal angles? There's something very, very, very simple I can say.
They're 360 degrees from each other.
Times some integer, right, where, n is equal to some, could be a negative number, could be 0, that would mean they were the same, or 1, or a positive integer. So these angles all will be within 360 degrees of each other. And let's see, I'm going to write this very formally here. Here we have some new Greek letters, alpha and beta. The relationship between A and B, if A and B are coterminal, is A equals B plus 360 degrees times n, where n is an integer. Okay? Does everyone understand what I mean by this? I'm not just reading this, I really wonder. Does everyone know what I mean when I put in brackets this list of numbers?
Always on.
Yeah, it just goes on. This is all the integers here.
So it's just ended from -2,
No, from,
Minus infinity.
they just keep going, -3, -4. The 3 dots are called an ellipsis.
So okay, these numbers don't include the.
Doesn't include fractional numbers or
Okay.
decimals, it's just the integers.
Okay.
For those of you who are going on in mathematics, we have a symbol for this set of numbers. It looks like a Z. And if any of you are taking German,
Yeah, that's me.
okay, okay.
That's mean the whole
Salen,
number.
Salen.
Yeah, which means.
Salen, which is German word for number, right?
Yeah.
Integer. Yeah. So if you go on in mathematics,
It means like a whole number
a
without.
whole number,
Yeah.
yes. Yeah. Okay. Those who are getting excited about this, we use this symbol here. It's an R, fancy R to mean the real numbers, the numbers on the number line. Okay, enough digression. All right. Okay, here we have some examples. I guess I'm supposed to do these. So, okay, find the length of an arc of a circle with radius 10 meters, with the tens and central angle of 30 degrees. You don't have to do this. You're going to watch me do this. I'm going to try and model this for you. So, of course, the first thing to do whenever you see a picture, a problem like this, is draw a picture, right? A picture is worth 1,000 words. Right? So, here we have a 30-degree angle. We're going to have a circle. And the radius is 10 meters. And this is 30 degrees. I guess we've done this already, so I'm going to be brief about it. We want to convert the 30 degrees from degrees to radians, so we'll multiply it by pi over 180, which will give us pi over 6. You may recall I suggested that some of these conversions are going to be good to know. 30 degrees is pi over 6. That's a good one to know. And again, we're going to use that, the length of the arc, S, is just going to be r theta, or theta radians. So it's going to be 10 meters times pi over 6, or if you like, 5/3 pi meters. This is a case where the you want to keep the units. This is also a case, as soon as they put some kind of unit measure like this, it's kind of your choice, but you're certainly welcome to say, hey, what they really want is some kind of real number here. So let's, here's my clear. Where it is. So 5 divided by 3 times 5. So let's just say approximately 5.24 meters. Right.
Can you keep it?
No, sorry. I'll put it down in just a second. We good yet?
Oh, yeah, I got it.
Yeah, okay.
I just have a question.
Sure.
Why, or like for instance, right now you use the angle inside 30, and for this example you use the 350, or sorry, 270. Like why you use the outside one time and inside one time? Why you didn't use like
So-
330?
Good question. So, when you first study geometry, right, if you were given an angle like this, right, you just say, oh, that's 120 degrees. And if I said, no, actually the angle I was thinking of was this one. It's negative 240 degrees. You'd probably look at me kind of funny, right? But now we're dealing with these directed angles. And so as soon as we put it on the axis, right? Like this. Well, there's my axis. So now, I can be specific about it. I can say, in the case of that problem, it's not this angle, which is negative 90 degrees now. It's this angle. I think 270. In other words, an angle can have any value now. It's not limited to 360. It doesn't have to be positive. And again, what I mean by it is you start here, and however many degrees, I tell you that's how far you go in a positive direction or in a negative direction. Now I know it's a little confusing, so ask questions. Does that make sense yet? No, okay. Okay, I'm going to try it a little differently. Make believe this is the tire on a car you're looking at. The cylinder, right? And I'm going to turn it. Okay? So I could turn it 45 degrees and 90 degrees in this direction, or I could turn it 270 degrees in this direction. Now the tire ends up in the same place, but if you think about it, the car does not, right? Or I could say, well, I could go 90 degrees, or I could go 360 degrees and then another 90 degrees. The ray ends up in the same place, but the car moved a different amount. Does that help at all?
Yeah, okay, that makes sense.
You can, that's just one way to think of it. You can think there's an axle here, and how far am I turning it, right? That way of looking at it will come in handy shortly. Okay? Okay, I guess I'm just going to do one of these now. I guess we worked on these two. Find the area of a circle with central angles 60 degrees. This is something else. I don't know what this is. See what this turns out to be. You don't have anything like this.
Yeah.
This one, it's in your, it's
Yeah,
still
it's
a different one, different paper.
This isn't on your paper.
No,
This is on my paper.
Yeah.
Actually, this is badly worded. I should have caught this, because I don't know whether this wants the area of this 60-degree sector, or the area, it sounds like it wants the area of the whole circle, and then the 60 doesn't make sense. So I'm just going to change it. Find the area of the sector in a circle with central angle 60 degrees. The radius of the circle is 3 meters. Okay. So here we have a circle, radius 3 meters. And we just want the area of this portion, the 60-degree portion. And we know the area of the whole circle is going to be pi r squared, which is going to be pi times 9. But that's the area of the whole circle. We know the ratio of this sector to the area of the whole circle is going to be 60 over 360 degrees, which is 1/6. So the area is just going to be 1/6 times 9 pi, or 3/2 pi. This is the type of problem where I really don't want to see a decimal point. I don't really want you to get rid of pi, because I haven't, oh, wait a minute, I'm sorry, they stuck meters in there, all right, you can use a decimal. All right, and this is just that same problem again. Do we have any questions about this? Yes?
So earlier we talked about length of a sector, right? Or is that?
For a sector, you could talk about the radius of the circle
Yeah.
and the angle of the sector. Did that answer your question? Oh, I didn't think it did, but, okay, yes.
Are you gonna use those tricky wording in the exam?
No.
Like,
No,
if I write the first person.
because then I'll just get people, go, what do you mean by this? And I don't really want that during the quiz or test. Or if I get it, it's because I deserve it.
Okay.
Okay, we're going to cover one last topic here. Oh, let's see, maybe next time. I have a cute little video that shows you something we did, but it's not going to download, so I'm not going to do that. Okay. I'm supposed to have a demo here. See if I can find it. No. Of course not. Nope, it's not it either. Is that showing up? No, good. Let's put it on here. No. Oh. Now let you show, I'll show you what I'm trying to do here. doesn't seem to be working. This is supposed to be a link. And I'm supposed to have a demo here. And I don't. Maybe if I look at my source code. No, I can't do that either. All right,
I think it's in.
first,
Try to right click. Just right click on anywhere on the page.
I don't have a trackpad.
Just
There's no right click.
yeah, either two. Yeah. They're actually like exactly
No. Preview? I don't think so. No. All right, things to be corrected next, like Wednesday. All right, we're just going to move on. What I wanted to get with this demo is the idea that if you have something that is turning, there's two ways to think about how it's turning, right? You can take a point on the circumference, and that point is moving around at some linear velocity. But you can also look at this way. You can say the angle that that point is making is moving.
Sorry. We can see some kind of passwords and stuff there.
Oh.
I don't see it.
Oh, thank you.
Now we're gonna steal your account.
Please don't. Poor teacher. Take my life savings. All right. So, the first formula I want to show you here is that you should be familiar with this. Velocity is distance divided by time. Now, in this case, I'm using for distance s because it's this distance along the circle. Similarly,